Welcome automotive and tech enthusiasts. Do you want to build your own device for your vehicle, like a custom dashboard display or a smart sensor? Today, we're exploring the world of automotive device development. We'll explain key components, SOMs, SBCs, MCUs, and even briefly cover the software frameworks needed to make them work. We'll also compare solutions to help you choose the right one. But first, let's address the elephant in the room. Is this video AI generated? Well, if it were, you'd get clear, concise narration and a much better looking host. So let's hope it is AI generated. Anyway, let's get into it. First, let's define the core components of custom automotive devices. Let's start with the MCU, or microcontroller unit. It's a single chip with a processor, memory, and input-output ports. It's ideal for simple tasks, like controlling a car's seat adjustment motors or running a basic sensor. MCUs are cost-effective and power-efficient, but have limited processing power and are mostly limited to one task at a time. Next up, we have SBCs, or single-board computers. These are complete computers on a single board, with a CPU, RAM, storage, and connectivity like Wi-Fi or Bluetooth. SBCs are versatile for mid-complexity tasks, such as dashboards or infotainment systems, balancing power and ease of use. Think of these as a full-size computer in terms of what they can accomplish, but with performance limitations due to their smaller size. Moving on to SoCs, or system on a chip, a more powerful chip that integrates a processor, GPU, memory, and connectivity options like Wi-Fi or Bluetooth. SoCs are used for complex applications, such as infotainment systems or autonomous driving modules. These can handle multiple tasks at a time. You can't really have an SoC operate on its own unless you're planning to include it into a larger board. This finally brings us to SOMs, or System on Module, a pre-built device board that includes an SoC or MCU or both, plus RAM and storage and additional external ports and GPIOs. It's a ready-to-use solution that speeds up development, but can be exponentially more expensive and complex to work with. It will also require an off-the-shelf carrier board or a custom carrier board to provide necessary outputs like USB, power, and whatever else may be needed. In summary, MCUs for basic tasks, SBCs for advanced applications, and SOMs for faster development, where the complexity of engineering your own SoC-based board would outweigh the benefits of the project. Now let's compare hardware solutions for automotive projects and go over advantages and disadvantages for each, and when you would want to use either of these solutions. Let's start with MCU-based solutions like Arduino, ESP32, and Teensy. Pros of these devices are that they are affordable, ranging from $5 to $50. Relatively easy to develop for, with strong community support and extensive IDEs. Suitable for small tasks like controlling LEDs or reading sensors. Some of the cons are limited processing power, not ideal for graphics or complex computations. They are best for DIY projects like simple, custom gauges or basic OBD2 scanners. Our take is that you need to scale correctly with the needs of your project. Do you need something that will simply read a sensor and transmit data to another system? Grab something that's cheap and widely available with large software support and tutorials. Arduino shines here. If you need more power, grab an ESP32, which range from simple to dual core beasts. Or, if you want the boss of MCUs, grab a Teensy 4.0. Sometimes overkill is necessary and rewarding. A good rule of thumb is to exclude anything MCU related from graphics-intensive projects that would require HDMI, LVDS, or other advanced displays. The limit here is simple: small serial displays with low resolutions. And even this might land you in a world of trouble and require you to scale to something more advanced like LVGL. Next, let's take a look at SBC-based solutions like the Raspberry Pi, NVIDIA Jetson, and BeagleBone Black. The pros are that they are versatile, with prices from $35 to hundreds of dollars. They offer decent processing, connectivity, and OS support for tasks like dashboards or multimedia. Large communities provide tutorials and libraries. Cons are higher power consumption than MCUs. Larger size and cooling needs can be tricky in cars. They're best for mid-complexity projects like in-car media players or prototype dashboards. Our take: SBCs like Raspberry Pi are great for prototyping mid-level projects where you need more grunt than an MCU but aren't ready for SOM complexity. Something like the BeagleBone Black offers GPIO flexibility for automotive sensors. Just watch power usage and size. The Jetson Nano, for example, is small, but its carrier board and cooling solution make it impossible to integrate into tight spaces. Last but not least are SOM-based solutions from manufacturers like Toradex, Verisight, and many others. Some of the pros are ready to use with robust features, including automotive-grade options, reduced development time, flexibility for future module upgrades. On to the cons. More expensive, often easily $100 or higher. Complex hardware and software requirements. Look up the term full-stack developer to get started. They are best for professional applications like fleet management systems or high-performance infotainment systems. Our take: this is really your only option for complex, integrated product development. Verisight, for example, offers a SOM for every situation and environment. Careful consideration is still advised, as just because something is available in hardware, it doesn't necessarily make it available in software. For example, you may have 3 CAN ports available, but software may only let you use 1 at a time, or none at all, due to missing info and drivers. Now that we've taken a look at the hardware options, let's switch gears and go over software choices. These are critical to making these platforms work, and each has unique challenges. The phrase "software is where the magic is" was coined for a reason. All these platforms live or die by the software that's available to make them work, which in turn may or may not kill your project overnight. As usual, let's start with MCU software, like Arduino IDE, or more concisely, C and C++. Advantages: simple programming environments like Arduino IDE are beginner-friendly with extensive libraries for sensors and actuators. Pitfalls: debugging can be challenging due to limited tools. Libraries may have compatibility issues or bugs with no support or fixes in sight. Limitations: no operating system, so multitasking is difficult on certain platforms. Even platforms with multiple cores may have trouble multitasking due to limited documentation and incomplete libraries and code. Memory constraints limit complex applications. Scaling up to something like FreeRTOS, which offers complex multitasking solutions, has a steeper learning curve than most beginners are accustomed to. On to SBC software like Raspberry Pi OS and Ubuntu. Advantages: Linux-based systems like Raspberry Pi OS or Ubuntu support Python and other frameworks, with abundant tutorials for platforms like Raspberry Pi. You also have access to a full operating system with many built-in functionalities like Wi-Fi and Bluetooth. Pitfalls: configuring drivers for automotive use is time-consuming. System updates can cause compatibility issues, and boot times may be slow when compared with heavily customized solutions. Limitations: Linux is resource-intensive, impacting power efficiency. Real-time performance is generally unreliable for critical tasks. Missing drivers or limited documentation can cripple functionality. Finally, let's talk about SOM software like Yocto or other proprietary solutions. Advantages: pre-built operating system images are often provided, with some support for real-time applications. Yocto allows custom OS builds where everything can be customized, added, or removed. Pitfalls: proprietary software may have poor documentation or restrictive licensing. Yocto has a very steep learning curve for customization. Limitations: real-time support varies by module. Some are available with onboard MCUs that can communicate with the Linux side of the system. However, customization requires significant expertise, increasing development time. So, let's recap a little and see how this info helps with picking the right base for your project. Here's what you need to keep in mind when getting started with your automotive project. Prototype smart. Start with development boards like Arduino or Raspberry Pi to test ideas quickly and cheaply before building custom circuits or moving to larger boards like SBCs or SOMs. Always adequately manage power. Cars have limited power and not overly steady power. Always account for power usage in your design and ensure you are delivering constant and clean power to your project. Take a look at compliance standards. It will give you an idea of the standards manufacturers use to make devices. Sure, your custom device may not have to follow all of them, or maybe none at all, but you may want to keep an eye on factors that may impact your device's functionality. Which brings us to testing for durability. Simulate heat, vibration, and electromagnetic interference, EMI, to ensure your device survives real-world conditions. This is probably one of the biggest mistakes for new makers. They fail to account for temperature variations, extreme vibrations, and EMI. Sure, you can wire that rear view camera that you got online for $5, but that doesn't mean you'll get clear 4K video. In fact, you may get no video at all, or you may get some static with some video in it. Always check documentation. This one is important. Always check software and documentation availability before embarking on a project or picking specific hardware for your parts. Like we mentioned before, great hardware is useless if the necessary software to make it work is not available publicly or at all. If needed, inquire with the manufacturer if there is a roadmap to release updated software and documentation. Ensure future availability. We have access to amazing hardware nowadays, but that doesn't mean it will remain steady throughout coming years. Devices like Teensy and Raspberry Pi have sporadic availability, which makes them terrible for a large-scale project. If needed, order many parts in advance to account for future shortages or production changes. Manufacturers like Toradex and Verisight generally have a very long support window for their hardware, though that's also subject to change based on chip shortages and other economic conditions. So here we are. These steps highlight just the beginning of the many hurdles that need to be overcome to build reliable, efficient devices tailored for automotive use. Stuck on your project? Tap into online communities for help. The Arduino forum is a goldmine for MCU tips, while Reddit's embedded subreddit covers many SoC and SOM topics. Check the ROS community for AI and robotics tutorials. These free resources offer code samples, troubleshooting, and advice from pros. You can also have a chat with the many AI models available, though quick tip there, always double-check the wiring diagrams they provide. In the real world, shorting 12 volts to ground is where you head out and buy new hardware. In their world, it's a quick apology and on to the next mistake. Our suggestion is skipping AI in the initial phases of learning or only using it to get an overview of your project and refine requirements instead. Share your project challenges in the comments or head over to absolutecarmods.com to read about ours. If this was helpful, like, subscribe, and hit the bell for more brief tutorials and deep dives. Thanks for watching and happy building.